To transform equations from rectangular to polar, essentially we will rely on the formulas for conversions that we have for x and for y, which is r cosine theta and r sine theta essentially. And well, all we have to do is simply replace x with r cosine and y with r sine. That's it. And well, let's see. So number one, 2 times r cosine, because that's x, plus 3 times r sine equals to 5. So we're done with the conversion from rectangular to polar. Now the thing here is that we have to express r explicitly whenever possible. Let's see if it is the case. And notice on the left hand side we have a common factor of r. That is r times 2 cosine theta plus 3 sine theta equals to 5. And then we can divide 5 by that whole madness multiplying the r. And we should get r equals to 5 over 2 cosine plus 3 sine. That's it. Final answer. For letter B. Letter B, well, I mean, we have xy equals to 6xy equals to 7. Just replace x with r cosine, replace y with r sine. That's it. So that's going to be 6 r cosine times r sine. And that equals to 7. Well, some simplification you might want to do here is to multiply the r's. That's r squared. That's times 6 sine cosine equals 7. But in this case, we won't be able to get r by itself. And the reason to that is that, well, let's get r squared equals to 7 over 6 sine cosine.
Can we combine this into sine 2 theta?
Into 3 sine 2 theta, that could be a good way to simplify, yes. But okay, let me do that, because that's essentially, okay, r squared equals to 7 over 3 times 2, right? Because 6 is the same as 3 times 2. But 2 sine theta cosine theta, that's a good call. Well, 2 times sine theta cosine theta is an identity. That's the identity for double angle for sine 2 theta. You don't have to go all the way to this, but I mean, why not? But the issue here anyway is 3 times sine 2 theta. The issue here, we wouldn't be able to get r by itself because we have it squared. We would have to use the square root property. That will give us two solutions. Essentially negative root of plus or minus, rather, 7 over 3 sine 2 theta. And well, you don't want to write this plus minus function, just to leave it in implicit form. Now, if you still want to simplify a little further, you might want to write this sine 2 theta that it's in the denominator, move it to the numerator, 7/3 cosecant 2 theta. That's a good way to keep simplifying this, all right? And we're going to leave it like this. Letter C, which is essentially well, I don't want to spoil it yet. Well, what do we have? X minus 1 quantity squared plus y squared equals to 1. All right. So, I know what you might be thinking. Just substitute x with r cosine theta and y with r sine theta and do the simplification. Although that's all right to do, that's not my preferred way to go about it, because you will have to expand a binomial containing r cosine theta minus 1. And so what I'm going to do here instead, I'm going to expand the binomial while in rectangular. That's x squared minus 2x plus 1 plus y squared equals to 1. And well, number one, we can cancel those ones right here because they're the same on both sides. And we're going to be left with, well, I'm going to put the square terms together. X squared plus y squared minus 2x equals to 0. Okay? And well, I know what you might be thinking. Okay, replace x with r cosine theta, turn it into an r squared cosine squared theta, r squared sine theta, but we don't need to do all that because we know that x squared plus y squared equals to
R squared.
Just do that. All right. I mean, essentially, you should get the same if you go the other route. All right, but no need. So this is r squared, and replace this x with r cosine theta. And well, so that's r squared minus 2r cosine theta. Set it equal to 0. Solve for r squared equals to r cosine theta. But in this case, this is going to be a little weird for a while because, well, we have r squared, we have r's on both sides. And, okay, before simplifying this equation, let me take a detour back to algebra. How do we, okay, any ideas on how to solve this equation?
We move x to the left, and then we factor out x.
Factor out x. All right. I heard some of you saying to divide both sides by x, right? Is that like another alternative to solve the equation? Okay, let's go that route first. See what's going to happen. Divide both sides by x. I don't know why it's not legitimate. I mean, we are not making up any rules. I mean, we're not. So that's x squared equals to 1, and x equals plus minus the square root of 1, which is 1. But here is the problem. How many solutions do we have over here? And what's the degree of the equation? So we would be expecting to get 3 solutions, right? Where's the other solution? So the issue with solving these equations this way is that, well, we are potentially getting, well, we're getting into two issues. The number one issue is missing one piece of information, in this case one of those solutions. And number 2, we are potentially dividing by 0, and you know the whole story about division by 0, right? We cannot do that. So in this case, okay, let me cross this. That's not how we do. Instead, x cubed equals to x. Move the x to the other side, to the left side. Make it a GCF. And now we're going to have our 3 solutions. X equals 0, x equals -1, and x equals 1. Now check this out. Do you see this solution, x equals to 0?
Yeah.
Aren't we here really dividing by 0? So we are in that issue. So careful with those equations. However, okay, so this is an issue with. This is an issue in the rectangular system. However, that's not an issue in the rectangular system because, well, when you have a circle, you can have a circle of radius 0, which is essentially just the pole, isn't it? It's just the origin. So in this case, it's fine to divide by essentially or potentially 0, right? And that gives us the following equation. R equals to 2 cosine theta. So in this case, just to make a contrast, not safe, safe. Exactly. And in this case, well, in the polar system, a shape with a radius 0 is the pole, is the origin in this case, right?
This dot.
Exactly, it's a dot. So we're good. I know it's weird, but that's what it is. And in fact, well, isn't this the backwards version of this problem? Yep. All right, so that's a little bit of algebra in the polar system. What about analytic geometry? Well, so what do we have here? The different shapes. You don't have to memorize it. You don't have to write anything down on this. This is just going to be a visual thing. You won't be, asked for, draw the graph of a rose with 17 petals. No. So write the equation. No. You're not going to be asked anything. In fact, you're going to be given something, which is going to be the next section, and find the area inside of a cardioid, the area of a loop of a rose, or the arc length along the whole, along one, when we traverse these ones, etc. All right? Well, here is the thing. Well, so we have a circle that is represented by r equals to a. In the same way that we did the previous example in the previous page, r equals to 5. That was a circle of radius 5, center at the origin, which is, well, the center is the origin and 5 units. The second example that we did over here, it's r equals to 2 cosine theta. So in this case, bless you. So in this case, well, notice the shifting of the circle. It's to the right, and when it comes to sine, the shifting is vertically. That, well, you can relate to that. I mean, again, you're not expected to memorize all these ideas, but what I'm trying to do here is just to connect some ideas. Points on the unit circle. The x-coordinates, when you evaluate the trigonometric functions of the most common angles, you look at the x-coordinate to evaluate the cosine function, and you look at the y-coordinate to evaluate the sine function. Same connection here. Whenever we have a circle described as a sine, that's shifted along the y-coordinate. And same for cosine, it's shifted along the x-coordinate. So I think it's a pretty cool connection to see. The next classification of polar curves are the ones we call limitones, and the cardioids fall into that category. They're called cardioids because it looks like a heart, all right? But not quite like a heart. And then we have the roses right here, and the roses are the pretty cool ones, and there's a pretty cool pattern recognition for this. Well, so the equations are going to be r equals sine theta and cosine theta, a number multiplying them in front of them, and an n multiplying with the angle, in this case with theta. Well, here's the thing. Whenever we have n to be an odd number, that flower will have n number of petals. However, if the number that multiplies the angle is even, well, the number of flowers will be twice as many as that coefficient in the coefficient of theta. Well, for example, you can see the 2 theta here. How many flowers it has? I mean, how many petals it has? 4, right? It's twice as many. 3 theta, well, just 3 petals. 5 theta, just 5 petals. But 4 theta, twice as many, right? 8. Now, let me go to the graphing calculator, and okay, let me rate. Okay, see, the mode number 1 has to be in radians, and make sure to be in polar mode. All right. Then when you go to y equals, well, you will see these are equations. Let me clear from my lecture a couple nights ago. So this is r. Okay, let's see. Let me do 2 sine. Oh, come on. 2 sine. Oh, I see what's going on. Sine 6 theta. Okay. By looking at this equation, so this is going to be the graph of a flower, but how many petals is it going to have? Notice the coefficient is even. 12. All right, let's find out. Well, number 1, let me do some fit. But this calculation, well, these graphing calculators are a little weird at times because, well, in some cases we're not going to have this circular or smooth circular curves. You're going to look at this sort of swords right here. Well, to fix this, ask your calculator window to go at slower steps. Notice the step is 0.1 essentially. So I'm going to clear this, and I'm going to turn this into 0.01 to ask the calculator to plot more points. And that's going to fix the issue and make it a smoother curve. All right. So that's one example. I mean, I don't want to do like all of them, so I'll let you play with the different forms, put your favorite coefficients, etc. However, there's other fun curves right here, like what's it called? Let me do the butterfly curve. All right, let me do the butterfly. Get my notes. I'm gonna get my notes here, and All right. Yes, it's right here. Okay, so for the butterfly, let me clear all this, and that's going to be second e to the sine theta, close parentheses, and that's a minus 2 cosine 4 theta, and graph. Well, initially I'm not going to be able to see the whole thing, so again, let's zoom fit, and there it is. There's the butterfly. Let's see if I can modify this a little bit. Maybe turn this into a cosine. Let's see what happens with 8 theta. Nah, that doesn't look like a butterfly anymore. All right. So anyway, another pretty cool Valentine curve. That Valentine curve, that's going to look more like a heart rather than the cardioid that I showed you on the page right here. That doesn't look like really like a. That looks more like an, I don't know, maybe like an upside down apple, maybe minus the stem. And well, so careful with this one because this one involves absolute value function and it also involves the cotangent function. Well, so when typing these functions on the graphing calculator, well, let me clear this and let's go math. Num. The first function is the absolute value function, and let's do the tangent. And tangent theta, close parentheses, and we're going to raise this to the power that is, that's another absolute value function, but in this case we need the cotangent function, and unfortunately our graphing calculator is not equipped with a standalone button for the cotangent function, but we know our trigonometric identities, and we know that cotangent is the same as 1 over tangent, isn't it? That looks more like a heart, isn't it?
Oh my God.
We have 2 hearts in this case, right? We have 2 of them. Mm-hmm. Another Valentine curve. Well, let me do the other one. Let me do the Pac-Man one. Okay, Pac-Man. For Pac-Man, that's a 1 plus cosine theta raised to do the, whoops. Let me delete this one and, yes. And raise that to the 999 power and graph. Well, except for this sort of a tail here, that looks a lot like the Pac-Man curve, isn't it? Let me zoom it in a little bit. Zoom, fit. Sort of, right? Not quite, but sort of. So, and guys, you can Google up a bunch of other pretty cool shapes in the polar system. You know, like even more elaborate butterflies out there, more elaborate hearts. There's a bunch. Just Google them up. Just Google something like graphs, cool graphs in polar system. I mean, you will find a lot of pretty cool stuff out there. And that's about it for this section. And let's see, we're gonna do officially our last section for the semester, section 10.4, which is the calculus of polar coordinates. What we're gonna do here is find areas, arc lengths, and slopes. All right. So, we're going to start with finding the area under the curve, all right? So, so we need to develop the formula first. I mean, I could just give you the formula and go through the examples, but I think it would be pretty cool to get to see where is this formula coming from, really. So, number 1. Okay, back in Calculus 1. Just so we can have an idea of what we're going to do here. You know, when you have a function f of x between a and b, essentially we calculated the area, number 1, by partitioning into rectangles. All right. But of course, I mean, like 4 rectangles was not a good calculation for the area. Neither 8 of them, neither 25. You know, and these calculations became very tedious to do. I mean, finding essentially 8 values of a function, 25 values of a function. You don't want to do that really. And well, so Riemann came to the rescue in this case to add infinitely many areas of these rectangles, because in this case the best result, we get the best area by partitioning the area into infinitely many areas of rectangles. And in this case, well, we don't have time to add infinitely many calculations, right? Of course, so that's why we represent that using a limit as n approaches infinity. But well, that's the situation for the rectangular system, for the area under the curve. How are we going to do this in polar system? Well, so instead of finding areas of rectangles as we did in the rectangular system, in the polar system we're going to rely on finding areas of circular sectors. All right, for the simplest case, let me take the circular case. I mean, well, if you already know a formula to find the area inside of a circle. That's 2 pi r squared. But I mean, if we wanted to partition this into one circular sector plus the area of another circular sector plus the area of another circular sector, essentially add those circular sectors, and that's going to give us the total area, right? However, well, for the simplest case, which is the circle, that's the idea, and we already have a formula. However, not all shapes in polar look the same. They don't look circular, because, well, remember that butterfly, it's not circular. Remember that heart, that Valentine curve, no, that's not circular. So essentially we're going to have some other generic shape, which is some function r of theta, between, instead of integrating over an interval a and b, we're going to integrate over an interval delimited or bounded rather between 2 rays, and these 2 rays are the angles a and b, which actually I'm going to call this alpha and beta, just to stick with the correct notation that we're going to use later. Alright, so essentially what we're going to do here is find areas of circular sectors. So this is one circular sector. That's another circular sector, Well, let's describe. I mean, of course, I noticed this little gaps right here that I'm getting by not computing the correct area. It's the same situation that we had over here. These gaps right here when we did these approximations with triangles. But again, we can make it better by, guess what? Partitioning this region into infinitely many, but this time rectangular sectors, not rectangular, circular sectors, not rectangular sectors, right? So, and well, this sector is going to go from the angle 1 to the angle B, which is that's going to describe the delta theta. In the same way that we had a delta x in the rectangular system, which is the base, the length of the base of the rectangle, and then the height was given by the values of the function. So in this case, if you think of this as a rectangle, well, the height of the rectangle this time is the radius of that circular sector, and that's given by evaluating the function in the same way that the height of the rectangle was given by evaluating the function at the value of x. So relying on the formula for finding an area of a sector, which is here. Well, you learned that in trigonometry or even in basic geometry when you first got introduced to this. Well, so we're going to start with this. So area equals 1/2 r squared theta. Well, in our situation, this r, it's going to be the function f of theta, quantity squared, but this theta is not theta per se. It's actually going to be our delta theta. And let me call it a sub I. Sub I because it's the ith sector. I could use the first sector, the second sector, the 57th sector, the 35,024th sector, whatever it is, and from there add infinitely many of those. All right? So number one, the area will be approximately, so we do an approximation first, will be approximately the sum of all these sectors, right? But do you see the issue with what I'm doing here? Do you see these areas that are going outside of the region? That's an inaccurate result. So that's why we have this approximation from I going equal to 1 to n of 1/2 f of theta sub I quantity squared delta theta sub I. Well, that's an approximation. How do we make it the exact value? We turn the approximately into an equal by, check this out, by taking the limit as n approaching infinity and adding infinitely many of those areas. You know the whole story, you know the rest of the story. That's 1/2 the integral of f of theta squared d theta. And the limits of integration are going to be between alpha and beta. Instead of, I mean, a and b, but well, in this case, we are going to start using Greek letters for angles. You know, we usually use theta, phi, what else? Omega even. Alpha, beta, and gamma are very common letters to use that we use to denote angles. So that's how we construct the formula for finding the area under a curve described in the polar world. Essentially the same idea as in the rectangular, but instead of relying on finding areas on the rectangles, we're relying on finding areas of circular sectors, right? And well, that's the formula here. And again, for the sake of notation, I mean, to make it more compact, you can turn this f of theta as a function r, because r is a function of theta, all right? Just the same as y equals f of x. In this case, r is f of theta. So, how about we look at one example? So number one. So by the way, these examples are going to be long. Well, the first one is going to be all right. We're going to have time to cover the first example, but not the second example. These are going to be long because these are going to rely essentially on trigonometric integration, which is something we covered at the beginning of the somewhat at the beginning of the semester. We will recall a lot of the trigonometric identities, and well, you'll see. So number one, let's find the area enclosed by one loop of the four lead rows r equals cosine 2 theta. Well, I mean, they're also giving us the limits of integrations. What could go wrong? Actually, a lot. You'll see. So that's 1/2 integral from alpha to beta r squared to d theta. So far so good. There's no big deal. 1/2 from negative pi over 4. And that's the quantity square d theta, where the quantity square is cosine 2 theta. And well, I'm just going to clear the parentheses here. Negative pi over 4. And that's cosine squared 2 theta, d theta. All right. Well, we'll talk about the method of integration for this one. However, let's look at the geometry behind, yes. That's what we're going to do. And I'll show you why. Here is when I said what could go wrong about it, well, actually a lot can go wrong about this if we don't consider these pieces of information. Well, number one, check the area that we are trying to find. Notice we have some area below the x-axis, and we have some area above the x-axis. But here is the issue here. The issue with this is that areas below the x-axis, we know them to be negative, while areas above x-axis will be positive. So here is what can go wrong. Evaluate that integral as is, your final answer will be 0, which doesn't make sense because clearly we're seeing an area there, right? So that doesn't make sense that we get a 0 area. So in this case, just like she said, we're going to take advantage of the symmetry. So I'm going to evaluate the integral between 0 and pi over 4. So that's 1/2 the integral of cosine squared 2 theta d theta between 0 and pi over 4, and I'm going to multiply this by 2. Doing the symmetry thing is going to get us out of trouble of getting the 0 as a final answer, all right? So, yes, this is the problem when working in the polar system, guys. So, I don't remember getting these kind of issues back when we found areas or even volume surfaces, surface areas and the like. Of this kind of surfaces, right? So it's going to be an issue with this polar graph. So that's the integral from 0 to pi over 4 of cosine squared 2 theta. Number one. Okay, here is where we discuss the method of integration. So can we use substitution here?
No.
Unfortunately not. We wished we had a factor of sine multiplying the d theta, so it stands the u du part of the problem, but unfortunately we don't have it. So we will have to use identities, okay? So there's a couple of identities that, well, I called them power reduction formulas, but the textbook usually refer them as half angle formula. So when we have cosine squared theta, that's sine squared theta. Does anybody remember these formulas?
It's 1/2.
Uh-huh. Plus 2 theta. Uh-huh. That's one. Minus, all right? Okay. So these identities, yes, they're going to get us out of trouble here by reducing the power and leave us with a simpler integral. Essentially what these identities do is simplify the power or reduce the power at the cost of duplicating the angle. But that shouldn't be a big deal because we can easily integrate a function with a multiple angle. That doesn't matter. That's easy to do. So I'm going to replace this with, and I'm going to make a mistake on purpose here to see if you can catch it. Pi over 4, that's 1/2, 1 plus cosine 2 theta. 4 theta, right? It has to be 4 theta. That's the mistake I did. Because for a given angle, whenever we use the identity, we have to duplicate the angle. So in this case, we already have a 2 theta. When we use the power reduction formula, we need to duplicate that, all right? And, well, that becomes a 4 theta. It's time to write this in terms of two integrals. Cosine 4 theta d theta. And well, these two are really easy to integrate. Come on, the integral of d theta is just theta times 1/2 and plus 1/2 the integral of cosine, which is sine for theta, but I left a space for 1/4, right? And evaluate between 0 and pi over 4. Okay. Let me simplify the answer to the integral. And you know the drill for the rest of the problem. Fundamental theorem, upper limit minus lower limit. So that's 1/2 pi over 4 plus 1/8 sine of 4 pi over 4 minus 1/2 0 plus 1/8 sine of 4 times 0. Okay, that's a lot is going to get simplified really nicely because sine of 4 times 0 is the same as saying sine 0, which is 0. 1/2 times 0 is 0. Another, here the 4's cancel. Sine, we're left with sine pi, which is 0. Final answer then?
0.1 to
Pi over 8. Alright? Actually, need to leave this in exact form, in terms of pi, because I don't think, what's it called, Weber sign is going to take decimals. Unless otherwise specified, we need to leave them in exact form. So this is the area.
I don't know, but in the pi, it can be.
Yeah, of one petal. So now, what if they asked us to find the area of the entire rows? What would you do to get the area of the entire rows? Multiply by 4, because we have 4 petals in this case, right? So the area, and then the area of the entire flower will be equal to 4 times the area of one loop. In this case, 4 times pi over 8, which is pi over 2. Sound good? And I think it's a good place to quit for today, because the next problem